Welcome! Today we look at extrema under constraints. We have a function of two variables fx, y, which we want to extremize, but we are forced to be on a constrained curve. Let me just take an example. That's x and y. Just 1, 2. And we take a simple function like fxy is equal to x squared plus 2y squared. So this function, we can draw the level curves of this function. So I think it's something like that. It's a little bit longer here. It's a level curve, so ellipses. So these are the level curves where f is equal to constant. And now we have a constraint. Let me just call this g x, y. And we also take a simple function like x minus 2 squared plus y squared. And we assume this to be constant. This gives us a curve. So if this is equal to 2 here, and so this is 2, and then it's a circle of radius 1. So that's g. So now we are interested in the question, where on this curve is f maximal? So here in this case we can see that, right, that's a kind of an elliptic paraboloid here, and then we walk along a circle. So of course we are kind of highest here and then lowest here. So it's pretty clear from the picture here that here's the maximum and here's the minimum. But we want to derive this and mathematically describe what is going on. So what is important to realize is that the point here where the level curves are crossing transversely, we don't have a maximum or minimum. And that's kind of the analog of the Fermat principle. So analog to Fermat, it was Lagrange, however, who realized this first. If the level curves g of f, let me just write it like that, level curves of f cross g is equal to 1 transversely, then this point is neither a maximum nor a minimum. So for example, that happens at this point, x naught, y naught, that's a point here. And what we have is, at this point, we are crossing the level curves. We are actually marching up if we go in this direction. So we can describe this also using the gradient. The gradient will be the language. This is the gradient of f, and we have the gradient of g, which is here. You see the gradients are not parallel, even only if this is happening. So that's kind of the first thing. And this happens the gradient of f and the gradient of g are not parallel. So that happens here, and so we can turn this around, and that's the principle. So if the gradient of f is parallel to the gradient of g, then we have a chance. for the maximum on a minimum. So that's the condition which we mathematically can describe using the Lagrange equations, and that's what I write down. This to be parallel means the gradient of f is a multiple of the gradient of g, and g is equal to constant. So these are called the Lagrange equations. So this is a new letter, that's a Greek letter lambda, because of Lagrange. So that's a parameter which we just, it's called Lagrange multiplier. So lambda is called the Lagrange multiplier. And usually we are not interested in this lambda, but we are interested in x and y. And so these are three equations, right? So these are two equations, this is one equation, so 1, 2, 3. We have three equations, fx is lambda gx, fy is lambda gy, and g is equal to constant. So this gives us a system of equations which we can solve. And let me just do that quickly here. So we write down these Lagrange equations. So fx is 2x is equal to lambda times 2 times x minus 2. Fy is equal to 4y. This is equal to lambda times 2y. And then please write always the third equation together. So it's always good to have this all together. We have a system of equations here. 3 equations and 3 unknowns. This is in general quite tough. So these are nonlinear equations, and already linear equations can be tough, as you know from linear algebra if you have taken linear algebra. And but these are nonlinear systems in general. But this is the equation 1, the equation 2, and the equation 3. Let me tell you how you actually solve this nicely. So what we want is, we want to get rid of lambda, eliminate lambda. The easiest thing is to divide through, but don't eliminate any of the, don't cross out any variables. So what we have is, we take 1 over 2. And this gives us here x over y. The lambda goes away, is equal to x minus 2 over y. And now we cross multiply. By the way, this just means that the cross product in 2 dimensions is 0, which is equivalent to the parallel property of the two vectors. So we are not doing anything wrong here. The books tell you not to do that, but you can do that very nicely, and I urge you to do that to get rid of lambda immediately, the first step. And then we can simplify this. And so if this is the equation which we can simplify. So 2yx, and then so we get actually, we take that on the other side, we get 4y is yx. And so what are the possibilities here? So either y is equal to 0, and if y is not equal to 0, we see x is equal to, so we see here that y is equal to 0. So if y is equal to 0, we see x is equal to 1 or 3. So from the equation 3, we see x is equal to 1 or 3. So these are these two points here. Or we see that when we divide by y, x is equal to 4, but that doesn't work. Right? X equal to 4 doesn't work with that constraint. So that's these are the only two solutions. So we have x, y is equal to 1, 0, and x, y is equal to 3, 0. So these are the extrema. And in order to see which one is the maximum and which is the minimum, you just plug it into the function. So what we see is the function value here is equal to 1. And here at 3, 0, the function value is equal to 9. So here the function value is bigger. So this is the maximum, and this is the minimum. So don't use any second derivative test. We would have to use some directional derivatives, second directional derivatives stuff. We are not doing this here. But that's the method, and we are going to look at a few more examples. Okay, many of these problems are very applied. Like we have something we want to, a volume we want to extremize. Like if we have a can and we want to extremize this. So here, it's not a can, but we have a jar and we want to extremize it. And so let me just set up the problem. So we have a height and we have a radius. And so let's just write down V R H. This is the volume. And the volume, you know, is R. This is the base area times the height. Pi R height. And then we have the area of the. So the area is the area of the mantle, which is 2 pi h. 2 pi RH. That's the circumference times h. If you would cut it up, we would just get a rectangle of that area. And then we have also the top and the bottom. 2 pi r squared. Okay, let's just assume we want to fix. Usually, what you have is that the volume is fixed. You want to minimize the material cost when the volume is fixed. So let's assume this is equal to pi. Volume is fixed. So that's the G, and that's what we want to extremize. Minimize A. Minimize A. So the material cost. So let's just look what the equations tell us. The equations tell us that AR, so now we have two variables, AR is lambda times VR, and AH is lambda times VH, and we have the constraint, we have VRH is equal to pi. So these are the Lagrange equations. Let's just write them down in more detail here with the function. AR is equal to 2 pi h plus 4 pi r is lambda times, and then VR is 2 pi RH, and if we take this AH is 2 pi r is equal to lambda times pi r squared, and then we have we can also cancel this r squared h. H is equal to 1. So these are the Lagrange equations. There are three equations. 1, 2, 3. Now, again, we want to get rid of lambda. Cannot stress this enough. People always get stressed out and tangled up with lambda. You don't want lambda. You want it away. So what we do is we take 1 over 2 pi h plus 4 pi r over 2 pi r. The lambda is gone on the right hand side. The pi is gone. 2rh over r squared. Note that I didn't divide anything through. I didn't divide by r here. R could be 0, and so let's just see. I think that's okay. So, but we can cross multiply, and we don't do anything wrong here. So we get 2 pi r squared h plus 4 pi r cubed is 4 pi r squared h. So the 2 pi r squared h, and this is, so we have 4 pi r cubed is 2 pi r squared h. And now we want to get rid of this r cubed. We want to eliminate this. So notice that r equal to 0 is not possible because of the constraint. So on that constraint here, third equation, that doesn't work with. So we can divide by r. So then we can also divide by that. We get 2. So we get 2r is equal to h. And that's really what we want. We want to have a relation between r and h and no lambda anymore. So that gives us an information which we can now plug in into the third equation. So we plug it into the third equation, and then we have r squared times h, which is 2r, is equal to 1. So r is equal to the cube root of 1/2, and h is just twice of that. So this is our solution. So let's just look. Is this an optimal jar, an optimal can? What we have here seen is that h is actually just 2r. So 2r is the diameter. So if you look at this can from the side, so this can is actually, so this is 2r and this is h. If you look at this can from the side, then it's just the maximum is actually just when we have a equal. So in this case, that's not optimal. Also, the usual cans you have are not optimal. Well, I didn't progress so fast. Okay, the next story is about entropy. It's something which has been developed here, kind of locally. Claude Shannon, you see him here in this book, a recent biography. He lived nearby in Winchester. It's a nice place, the Mystic Lakes. And you see him here with his wife, who was also a mathematician. So they tinkered in the house. And it's a pretty amazing person. So he came up with the concept of entropy, and so let's look at this. Let's look at this concept, and it shows that this Lagrange problem can be done also with more variables. So what we have is a dice. So dice. The dice. So there are 6 sides, and maybe it's not a fair dice, but the probability that phase 1 appears is P1. So Pk is the probability phase K turns up. So Claude Shannon, father of information theory, defined entropy kind of independent of in statistical mechanics. Boltzmann also came up with the same concept, but that's a discrete notion here. So what we have is S, and what we do is we take minus P1 and then log P1 minus P2 log P2 minus P3 log P3 minus P4 log P4 minus P5 log P5 minus P6 log P6. So of course that's not how we usually write this down. We can write this down usually with a sum notation. That's the sum minus k is equal to 1 to 6 pk log pk. That's a more concise way to write this sum out. But you see we have 6 variables. Not 2 or 3 like usually in multivariable calculus, but we have 6 variables. And the log, of course, is always the natural log. And so now what we want to do is we want to actually maximize the entropy. But there is a catch, and the catch is that we have a constraint. We have a constraint which is given by the fact that these are probabilities. And the constraint is that P1 plus P2 plus P3 plus P4 plus P5. So we have a constraint which is P1 plus P2 plus P3 plus P4 plus P5 plus P6 is equal to 1. So that's the function which we want to extremize, and that's the constraint, the total probability, let's call it maybe T. So we want to extremize this. So now let's look at the Lagrange equations. So the Lagrange equations have now, there are 7 equations and 7 unknowns. So this is a Lagrange problem. For 7 equations, unknowns. So it's P1 until P6 and lambda. So let's just write this down. So first of all, we have the derivative S. Let's just write this down first of all. When we have just a side computation. So f of x is equal to minus x times log x. What is f prime of x, the derivative? So we have to use the product rule. This is minus the log of x. And then we take minus, and then we take x times 1 over x minus 1. So that comes handy if we actually compute here the derivative here. The derivative, the partial derivative of s with respect to p1, for example, s p1 is equal to minus log p1 minus 1. And of course we have tp1 is equal to 1. And when we take the derivative of this with respect to p1, we get equal to 1. So the Lagrange equations are now the Lagrange equations are, so we can write them down. So it's minus log p1 minus 1 is equal to lambda times 1, minus log p2 minus 1 is lambda times 1, minus log p3 minus 1 is lambda times 1, minus log p4 minus 1 is lambda times 1. You get the idea. Minus log p5 minus 1 is lambda times 1, minus log p6 minus 1 is lambda times 1. And then we have also the constraint, which is just p1 plus p2 plus p6 is equal to 1. So these are the 7 equations. They look scary, but it's actually very easy, because what we see is when we eliminate this, we kind of take, we can also subtract instead of dividing. We subtract the 2. We see that log p1 is equal to log p2. So this is the first equation, this is the second equation, this is the 6th equation, this is the 7th equation. So if you take 1 minus 2 tells us log p1 is equal to log p2, and then exponentiate, so we get p1 is equal to p2. Etc., etc. We can take 1 minus 3, and then we see p1 is equal to p3, etc. So we see that p1 is equal to p2 is equal to p6. So they all have to be equal. Now we can plug it into the constraint. If you plug it into the constraint, you see that the probability is equal to 1/6 for each. So we plug it into the seventh equation, so we see P1 is equal to P2 is equal to P6 is equal to 1/6. So we see the fair dice. So the fair dice has maximal entropy. It's usually these symmetric situations have maximal entropy, and it's the least information you can get out of this. If you cheat, you make the dice, you know, the asymmetric, then you can gain from it. You have some information. So it has to do with information. And in the handout, I show you when you kind of take the entropy and you combine it with free energy, then you get with energy you get free energy, and that's important in chemistry. There's a little catch with the Lagrange equations. So it's not quite true that if you have a maximum or minimum that the Lagrange equations are necessarily satisfied, even we have smooth functions. So the precise statement is if x naught, y naught is maximum or minimum, under the constraint g is equal to c, then either the Lagrange equations hold, gradient of f is lambda times the gradient of g is equal to constant, or, and that's another thing, it's also possible that the gradient of g is equal to 0. And this also means that the gradient of f and the gradient of g are parallel, but that's not possible here, because that would force us also that the gradient of f is equal to 0. So it's kind of just because we put the lambda on that side, this asymmetry forces us also to look at, sometimes to look at that. I mean, it's just an example here. You don't have to worry about this too much. So let's just take fxy is equal to x, and gxy is equal to, now I have to think, is x squared no, x cubed minus y squared is equal to 0. So I think that's the example we want to look at. So this is the constraint, that's what we want to maximize, and the picture is like that. So that's a nice cusp. So the function f here is this function here. So this is f is equal to constant, x is equal to constant, and then the constraint is y squared is equal to x cubed. This means x is equal to y to the 2/3. So x is equal to y to the 2/3, or we can take 1/3 squared, or we can take y squared. So that's always bigger or equal to 0. So that's a beautiful. It's like the coffee cup caustic which you have seen. It's kind of the same type of singularity here. So that's g is equal to 0. Now, if you look at this situation, you see immediately that 0, 0 is the minimum, right? 0, 0 is the minimum. Of the problem. Right, x cannot be smaller than 0, and it's always bigger except here. So that's the unique minimum here. So there's no other critical point, no other point which we have to consider. But let's look at the Lagrange equations. The Lagrange equations tells us Lagrange equations tell us that 1 is equal to lambda times 3x squared, and 0 is equal to lambda times minus 2y, and then we have x cubed minus y squared is equal to 0. So what does that actually mean? So if you look at that, This second equation tells us that either y is equal to 0 or lambda is equal to 0. But, so this is the first equation, this is the second equation, this is the third equation. So this tells us lambda is equal to 0 or y is equal to 0. So if lambda is equal to 0, when lambda is equal to 0, then that's not possible. That's not possible. That clashes with number 1. Right? Lambda is equal to 0 is not possible. So it has to be that y is equal to 0. But if y is equal to 0, what do we see? This implies from the third equation that x is equal to 0. But if x is equal to 0, this clashes with 1. Clashes with 1. This means clash. So doesn't work together. So you see that this has no solutions. This is a system of equation for 3 unknowns which doesn't have a solution. So the Lagrange equations are not satisfied. Still, we have a nice minimum, and the functions are very nice. These are polynomials. Okay, let's look at the following engineering problem. And this also shows the power of these Lagrange equations. We can also have more than one constraint, not only one constraint, but 2 constraints. We can have 1,000 equations and 755 constraints. So it's a very, very powerful framework. But what we have is we have 3 variables. Let's just assume that we want to maximize the volume of this. So volume. So this is equal to x, y, z. But now we have some constraints, and we assume we have a box which has 4 plus 1 sides, so it's 5 pieces. And so this is the area which is given. So area of x, y, z is equal to xy plus, and then 2yz plus 2xz. And let's assume this is equal to 12. So that's kind of some material cost for the side. But then we have also some kind of, stiffness here, which comes in from some maybe metal bars, or which makes this strong. And so we have also a length here, x, y, z, which is just 2x plus 2y plus 4. So 2x plus 2y plus 4z. And let's just assume this is equal to something else, maybe 8. So what we have is something to extremize. This is the function to extremize. And these are the constraints. So there is a general framework also here. Let me just write it down here. So we have f, x, y, z, which we want to extremize, and then g is equal to c and h equal to d are the constraints when we want to maximize or minimize such an equation. What we can write down is the gradient of f is lambda times the gradient of g plus another constant times the gradient of h, and then g is equal to c, h is equal to d. So mu is another Greek letter. Just after L comes, after lambda comes mu. And so let's just see. What we have is these are 3 equations, 4 equations. These are 5 equations. Three equations, 4, 5, and 5 unknowns. So we have x, y, z, lambda, mu. So that's it. So you rarely see such examples because they just, are very hard in general to do. I'm actually not even sure. I just made this up. I don't know whether this actually works. Just let's see whether we can actually solve this. Let's just see. So the gradient of f. So what we have to do is fx. So we have y z is equal to lambda times and then we take the derivative with respect to x here, so y plus z, and then plus mu times 2. So that's the derivative of L with respect to x. And then we take with respect to y, we get xc is equal to lambda times x plus z plus mu times 2. And then the last one is xy is lambda times, and then we take the derivative with respect to z, we get 2y. Oh, there was a 2 here. There was always a 2 here. And then we get 2y plus 2z plus mu times 4. And then we have the constraints xy plus 2yz plus 2xc is equal to 12, and 2x plus 2y plus 4z is equal to 8. So these are 5 equations from 5 unknowns. Usually you solve this with a computer, and otherwise it's kind of, it can be hard.